We're into chapter 5, and we're going to actually look at a solution, separation of variables. And actually, from Calculus 1, you've heard of this, okay? In Calculus 1, in the differential equations chapter, it solves the problem of, say, f prime equals k times f. And the idea there is that you divide both sides by f and you get f prime over f equals k. And then what we did was we integrated both sides with respect to t. So we integrated, and we had f prime over f dt is equal to the integral of k dt. So this was calculus 1. And we did substitution of variables, and this just becomes on this side df over f, so that we get a natural log there. And on this side we get our kt plus an arbitrary constant. So we'd have natural log of the absolute value of f is kt plus c, and then I exponentiate both sides. We got the absolute value of f is e to the kt times e to the c, which I could rewrite as, say, c1 or something. But that was in calculus 1, the idea of separation of variables. And here it's similar, and actually then we get one solution that is one part of our solution that actually goes follows this derivation from calculus 1 explicitly, but more generally, remember we're trying to find to our boundary value problem. So we've got u sub t equals alpha squared u sub x, and we'll just have just make it easy on us and have that go between 0 and 1, and t goes to infinity. Boundary conditions, we'll just use homogeneous boundary conditions. So we'll have u at 0 and t is equal to 0, and u at 1 and t is equal to 0. And that's for all t. And then our initial condition, we'll keep that as general. So we've got u of x and 0 as just some phi of x. And that's for 0 less than or equal to x less than or equal to 1. Okay. So that's our problem. So what we're going to do, though, is we're going to assume u of x and t is actually some x of x times t of t. Okay, we're going to assume that actually this is the separable part here, is that we're going to assume that the solution is actually a function of x times a function of t. And there'd be some constants multiplied in here somewhere, but for now, we have our function of x times a function of t. And now more generally, what we find is that when we do this, actually, u of x and t is the sum of a bunch of these, Could be an infinite number, but it may not be. But there's our constant, some a sub n, and then an x sub n of x, and a t sub n of t. So there's going to be possibly an infinite number of these pairs of multiplied functions, but we'll get to that, and we'll just we'll end up using technology to do this, but we'll show the derivation here as to kind of what happens. So okay, so we're going to start here, and we're going to get to something like this. But so if we start there, then if we say u of x and t is some x, again, let's not worry about the constant for the moment, and t of t, like that. Then if I want to find u sub t, right, that would just be x of x, and then t prime. Like that. And if I want u sub xx, that would just be x double prime of x times t. Okay, that's a nice thing. If we really do have solutions like this, then this is very convenient because these are just regular derivatives. And so then, for our u sub t equals alpha squared u sub xx, on the left-hand side we have our x of x, not x of t, x of x times t prime of t equals then alpha squared x double prime of x t of t. And now we do something similar with the separation of variables we did in Calculus 1. And I can write this as t prime of t over alpha squared t of t. And the alpha squared could stick with either one, but it just typically they write it with the t here, is equal to, and then I've got my x double prime here, over x of x. Okay, so we get that separation. But now this has to be true for all t and x. But if that's true for all t and x, those must be constants. And so what we have is that t prime of t alpha squared t of t would be equal to x double prime of x over x of x. But then that's got to be some constant. We'll call it k. And so now if we take each of the, so we'll take, this with the k, and then we'll take that with the k. And if we do that, I can multiply both sides by the alpha squared t times the k and bring that over. So I get alpha squared, well, I guess I'll do it like the book does. They have a k first. So k alpha squared t equals 0. So we get that from this one. And then similarly, we would have x double prime minus kx is equal to 0. Okay. And, you know, as I, now they make a convention where they point out that, let's see, that, well, if we go back here, so let's, for instance, look at this solution. Okay, because we've kind of done that, right? This is the T prime over T is equal to K alpha squared, like that. And so what we see back here, got to come all the way back here, but notice that that KT stuff that we did, K, you know, K here in this case is either positive or negative. But you see, if K is positive, okay, so if we go here and we say K is greater than 0, then our solution is going to go to infinity, right? So it's actually really not going to make much sense if it goes to infinity. And so this would have t going to infinity as little t goes to infinity. Because again, we would have, you know, e to the kt here. And you know, that doesn't really make sense for our physical situation, right? We've had these things that we've intuitively looked at and said, you know, they go to some steady state solution. Well, so this isn't going to happen. And so K has to be less than 0, okay, to make any sense. And so what they do in the text is they just say, well, we'll let K equal minus lambda squared. So now that is definitely less than 0. And so they'll end up writing these as, since we had a minus, now we've got a t prime plus lambda squared alpha squared t equals 0, and an x double prime plus lambda squared x equals 0. Okay, so we have both of those, and the solutions to these, we already know the solution to this one basically. Okay, it is in this case t, and I say basically because, you know, I went through it real fast, that this is what we did in Calculus 1, but this is some constant a e to the negative lambda squared alpha squared t, like that, and a is an arbitrary constant. Now, what we don't know from Calculus 1, we didn't solve this in Calculus 1, but x is equal to, and again, we can kind of check to see that that would be the case. Now, the book does this. They put an A here. I wish they wouldn't, because they've got an A up here, right? You know, so they're not the same A. But we have a sine lambda x, and then plus b cosine lambda x. And you know, if you check these, try putting sine lambda x in here, take the second derivative, right? And what you get is the second derivative of sine lambda x is minus lambda squared sine lambda x. And so you see you'll have a minus lambda squared here, a plus lambda squared there, and we will indeed get 0. Similarly, if you take the second derivative with the cosine here, you'll get a minus lambda squared cosine lambda x. And so same thing for that, those both work. And so these are the two solutions. And so, you know, what we would see then is our u of x and t is just the product of this thing. And they get rid of this a because, well, when I multiply, I'll have a a squared and a ab, just rename those. And so we get e to the minus lambda squared alpha squared t from right here. And again, I'm moving the arbitrary constant inside, and we'll just call it an a sine lambda x plus b cosine lambda x. And there's our solution. So great. Now, that does not take into account the boundary conditions nor the initial conditions, but it's a solution. It's a general solution, and so it doesn't matter what our initial condition is, or for that matter, boundary conditions. We'll always start with this. So that's kind of nice. I mean, you know, there's always a solution. But now, if we look at the boundary conditions, remember that these are homogeneous boundary conditions. And so we've got u of 0, t. Okay, now, so if we put in u of 0, t, so 0 for x, notice what happens is we get e to the minus lambda squared alpha squared t. Okay, we get that from right there. But now if I let x equal 0, sine is 0 and cosine is 1. And so I just get times b. And that, again, our boundary conditions are homogeneous. That has to equal 0, which means that b equals 0. Okay, so with homogeneous boundary conditions, right away we see that actually now we've got our first part. With the left-hand boundary condition that at 0 we get 0. We're now down to u of x t is equal to e to the minus lambda squared alpha squared t, and then a times sine of lambda x. So it's getting simpler. Okay, now on the other side, we have that u of 1 and t. Well, that's e to the minus lambda squared alpha squared t. We still have a, so a, but now it's sine lambda. That's equal to 0. Well, I guess a could be 0, but that would be pretty boring. And so what we have is that sine of lambda has to be 0. And so now we know, that happens when lambda is any integer multiple of pi. So it's just some k times pi. Well, let's see. Let's not use k because we were using k before. Gosh, what? How about n times pi? That would be good. Some n times pi. Now, and that could be plus or minus, but remember that sine of, any, lambda, we'll just say lambda is equal to sine of is equal to minus sine of minus lambda. It's an odd function. And so, really we don't need the negatives in here. We can do all this. Let's just worry about the positives. And so we're going to have lambda could be any n times pi, where n is equal to 1, 2, 3. Again, 0 would make no sense because you just get identically 0, but we have this. And we got rid of this because of the arbitrary constants, okay? Because who cares if it's a plus or minus? So, so using the fact that we've got an odd function, we can just substitute and we can now knock it down to this. And so what that means, this is their equation 5.2 in the text. Each un, so we said there could be an infinite number of these possibly, is just some a sub n, which we'll have to figure out, e to the minus, and they just go ahead and make that substitution of n pi, so n pi alpha squared, okay, t, and then sine of n pi x. And n can be 1, 2, and so on, up to infinity. So there are our possibly infinite number of solutions. Again, it depends on the initial conditions. So for instance, suppose your initial condition was simply that u of x0 was equal to sine of 2 pi x. Oh, well, then a sub 2, right, for n equal 2, a sub 2 would equal 1, and a sub I would equal 0 for I not equal to 2, right? And that would fit that. So, depending on your initial condition, this could actually be quite easy to solve, and so we would have u of x and t being, again, a2 is 1, everything else is 0, so we would just get e and t, n is 2, so minus 2 pi alpha squared t sine of 2 pi x. So again, with the right initial condition, these might be really easy. With a different initial condition, we'll see that this is a bit harder. But just so you see, depending on the initial condition, it could make it pretty simple because, again, this here's the initial condition, right? And we're saying sine of 2 pi x is equal to, again, at the initial condition, t is 0. So that part just disappears, and so we get the sum of n equal 1 to infinity of a n sine of n pi x, like that. Well, sine of 2x, make that sine of 2x, everything else 0, right? So again, you know, depending on your initial condition, if your initial condition's in terms of sine functions like this, it becomes easy. You know, I could make it 5 sine 2 pi x, in which case that would mean that a sub 2 is equal to 5, right? And we would just get everything being 0 except a sub 2 being 5 and sine of 2 pi x. Okay, and so, you know, and I could have more of these. You know, I could have a 3 sine x, or sine pi x, right? Minus, let's go with 5 sine 5 pi x, right? Like that for my initial condition. This is our phi of x. And this would be simple. This would then just be my stuff over here, and I would need to multiply it by that e to the negative n pi. So again, I would need that for each of these, right? So in this case, I would have a e to the negative 3 pi alpha squared t, and then, oh, sorry, 3, I got mixed up. That's alpha 1, so, sorry, that was n equal 1, right? And so I would have my 3 out here in the sine pi x, and then here's n equal 5, so minus 5 e to the negative 5 pi alpha squared t sine 5 pi x. Okay, so as long as these are sines, it's really not too bad. Okay, so those are some examples of that. Now, you know, what if it's not sine functions? Well, they go through a derivation. We're not, you know, I'm not going to worry about the derivation, other than to give you the bottom line is that each, so, you know, if phi of x is not, you know, some sort of sum of a, and I'm going to use a sub I pi x, like that. If it's not that, then your a sub n's are actually integrals, and they're 2 times the integral from 0 to 1 of whatever phi of x is, sine n pi x dx. So quite, you know, I mean, right? And you could have an infinite number of these, and actually, typically, if phi of x is not trig functions, in particular sines and cosines, then indeed you will have an infinite number of these. So that gets kind of hard to pin down. But just, you know, to point out, you know, if you had something like phi of x is equal to 1, which actually wouldn't make a lot of sense with homogeneous boundary conditions at 0, but if it is, and one of your homework problems just mentions this, if it's 1, then you know, a sub 1 would just be 2 times the integral from 0 to 1 of sine of pi x dx. Okay, and that's an integration by substitution. Similarly, a sub 2 would be 2 integral from 0 to 1 of sine 2 pi x dx. And so that would be a sub 2 and so forth. And so, you would have this a sub 1 times e to the minus alpha, because we haven't been told what alpha is, pi alpha squared t, and then sine of pi x, and then plus a sub 2 and e to the minus 2 pi alpha squared t sine 2 pi x, right? And it would just keep going, plus and so forth. And so we would have to come up with what the heck those integrals are. But actually we could, we can do that as well. These are going to fit a nice pattern. And so you could actually get a nice summation here on this. Okay, but that is the solution. That's how we get it from phi of x here. Either if phi of x is nice stuff, and by nice stuff I mean, sine of some nice positive integer times pi x, then we'll get pretty simple solution to write down. It'll just be in terms of these pieces of phi of x, and then we'll have to toss in our t terms, our parts with time. But that's it. And then if it's phi of x, well, we've got lots of integrals to do. But so I've got some technology, and we'll have another video on using the technology to actually generate these infinite sums, and then try to plot them so we can see the solutions. Okay, so that is separation of variables and where it brings us. And so we're not gonna be dealing with deriving it all the time or anything like that. We're just going to use this form of this solution.